What about a slightly more interesting and complicated example? How about the example that is everyone's favourite, the damped driven oscillator? So we've got some input here, which is a force, and the output here is the position, and the force drives a mass m with spring constant k and some damping with damping rate r. And we know from previous courses that we can write down an equation that has mass times acceleration, the force due to damping, the force due to the spring, and the driving force. We can rearrange this a little, dividing through by the mass and having a damping rate gamma and the natural frequency omega naught squared, defined like this. And then we know also we can find a solution to this equation in the case where the driving force is harmonic. So it's written like this: some force with some amplitude f naught and some harmonic driving frequency with frequency capital omega. In this case, the position of the mass can be given by the decaying transient solution that decays with time constant tau, where tau is defined like this, and a frequency omega dashed, defined like this. And then this part here is the driven solution, the steady state response, that depends on the force and the driving frequency. And this is the solution to the homogeneous equation, so it's known as the transient response or the complementary function. And this part here is known as the particular integral. It's the response to the ideal harmonic driving. Okay, so that's the part that we have seen before. Let's attack this from a different direction. So, let's go back to the differential equation and start playing with Fourier transforms. Here is our equation. When we take a Fourier transform on both sides, this double differential here gives us an I omega squared, a single I omega here, and then on this side the Fourier transform of the force, and the position x has been Fourier transformed as well. And this we can solve for the Fourier transform of the position x being related to the force f of omega with this thing here, which is now the transfer function. So just as before, we have an output x is equal to the input, which is a force, and the transfer function g of omega in the middle, which is defined like that. Now in mechanics, this transfer function that relates the force to the position is known as the mechanical susceptibility and is often written as chi of omega. So g of omega is this thing we've introduced as the transfer function, but I should mention that in mechanics it's often called mechanical susceptibility and is given this symbol here, chi. What does this susceptibility look like? Well, it's a complex function. It's got an I here, so we can plot the absolute value here and the phase, and as we increase omega naught, that is, say, increasing the spring constant, this is what the susceptibility looks like. So here we're increasing omega naught, and we can see how this mechanical susceptibility changes as a function of omega naught. So the mechanical susceptibility has some resonance here, which is omega naught, and the phase changes from 0 to minus pi as you cross that resonance there. Okay, so let's now think about a specific force, that is the harmonic driving force that we've solved for previously in another course where we just did a time domain solution, but now we're going to do it using Fourier techniques. So here's our harmonic driving force. The Fourier transform of that harmonic driving force, capital F of omega, is given by this equation here, where this complex exponential gets transformed into a delta function with an offset, capital omega, and look out for the factor of 2 pi here as well. So that means in the Fourier domain, our position, capital X omega, is given by this expression here, where this now is the mechanical susceptibility, and this is our driving force. To find the time domain solution, we take the inverse transform, that is, little x of t would be the inverse transform of capital X of omega. And this looks really horrendous, but actually it's not, because we have a delta function in our integral, and because of the shifting property of the delta function, all that happens is we get this term here, this fraction, with all the little omegas replaced with capital omegas. And so we end up with the time domain solution looking like this. And you'll notice this is the same time domain solution we found previously. It is missing some part of the solution, which is the response to some initial conditions. So when you solve a differential equation, then there's the solution to the homogeneous equation, which you get via initial conditions, and then there's a solution to the driven part of the equation, which we call the particular integral. This part here is just the particular solution, so the response just to the driving. that's one of the features of this Fourier method, is it just gives you this part of the solution. If you want to go looking for response to initial conditions, then you need to use a different method. So just to summarize then, the Fourier method gives you the particular integral, which is the response to the force. To find the solution to the homogeneous equation that allows use of initial conditions, you can do this with integral transform methods as well, but you need to use a Laplace transform. And with Laplace transforms, there's a clean way of introducing these initial conditions. Okay, what if we have a delta kick driving force? So now the f of t is going to be delta t, and so the Fourier transform is unity. So that means the position in the Fourier domain, x of omega, is given by this. So the inverse transform will tell us the impulse response of our mechanical oscillator. That is the inverse transform of all of this here, or we can write it as the inverse transform of this expression here. Now we're going to assume that we're in an underdamped regime, and then this is actually in our table of Fourier transforms, which allows us to just write down the solution that the impulse response, little x of t, is given by this expression here. So we have a unit step function, so that means before time 0, everything is 0. Then after time 0, we have a decaying exponential multiplied by a sine wave. Omega dashed is given by this expression here. This tells us that when we delta kick the oscillator, we get a decaying sinusoid. And this is exactly the behavior we might expect when we have a solution that isn't being driven. So we give a mass some initial position or some initial velocity, we let it go, and we get a decaying sinusoidal oscillation. Now, a minute ago I said that the Fourier methods don't include transient response, and yet here apparently we have one. The trick here is that actually it's not the transient response, it's still the response to a force, but the force in this case is a delta kick. And when you give something a delta kick, you're just instantaneously imparting some velocity on it. In terms of initial conditions, they are implicitly assumed that they're both 0, so the initial position and initial velocity are both 0, which is why the response here is a sine function and not a cosine function or any other phase. We can't fit a phase to it because the initial conditions aren't included in this method. But here's a physics alert. A delta kick in force, so a force delta function, has an integral of 1. And the integral of force over time is the momentum. Therefore, what we're doing when we give it a delta kick is we're giving it 1 unit of momentum. We're saying that at time equal to 0, we're going to just give it m times v is equal to 1. That's equivalent of giving it an initial velocity of 1 on m. And so that's what this solution here is. It's if you delta kick your oscillator, you're giving it a initial unit of momentum and then watching its response. Now, just as we did for the circuit, we can use our impulse response function to generate a solution to any arbitrary driving force. So let's again consider the case of a top hat drive. Now, if we were to look at the Fourier domain solution, we would have the Fourier transform of our drive multiplied, which is a sinc function, multiplied by the mechanical susceptibility, and we have to find the inverse Fourier transform of this. That looks really hard. You might be able to do it numerically, but I don't think this is really something you can do analytically. So instead, we can do this sort of visually using a convolution of the impulse response function and the driving force. This is what we did before with the circuit. So here is the force in time. It's the impulse response function convolved with our driving force. And it looks like this. So here's our driving force coming along. It hits our oscillator and it starts responding. It oscillates a bit, and at some point here, the force is turned off, and from this point forward, the oscillator is just decaying with no driving force anymore. The parameters I've used in this simulation, by the way, are these here, in case you're interested in trying to reproduce these results in your own simulation.